Hello there, everyone. This is Mr. D coming to you with the Pathfinder Honor Tie-Dye Stage 6 of what I have set up. These stages are designed to follow a layout for the Pathfinder AY Honor called Tie-Dye. And this is the sixth one in the list, which has to do with secondary colors. I hope that you find it interesting. If you haven't yet, would you please mark my subscribe button at the bottom? And so you can get all the new stuff coming from the honors that I will be producing as we go down. I try to do one stage or two stages a day. I don't know where the Lord's going to take me. I don't know how many will get done and how many clubs across the world that God will take this to. So feel free to tell people about it, and God will bless you, I'm sure. Totally. So let's get started with this page, and let's bring it up. Okay, this is called Stage 6. Describe colors needed to make secondary colors while doing tie-dye. And I have a link I start off right here called Primary Colors are Red, Yellow, Blue. I ask you the question, is that correct? And there's a website that kind of clarifies the difference of these. Let's step over there for a second. As you can see, I think I listed some on my last one. Primary colors and what they do. And I believe it down here, it talks about what happens when you get secondary and you get the primary and the secondary. Now they talk about creating those secondaries by how they interact with each other. But this website, along with the one I mentioned down here a little bit low, let's see where it's at. It's probably on the next website, but I have some more information. Let's go ahead and read through this and see what you get out of it. Starts off with this website listed for how stuff works can help you have a better and clearer view of secondary colors. Orange, green, and purple are called secondary colors, and they are made up from the primary colors. And as you can see, where you have red, yellow, and blue, they mix red with yellow or yellow with blue or red with blue, and they come up with these colors called orange, green, and purple. These are the colors I believe that they refer to as secondary colors. Now, let's step out for a second. This chart you see behind me, I'm going to include in my list of files, which I've showed you is on the main screen of the tie-dye. And it goes through the combinations of the colors and what makes them up, like when you use on acrylics, what they're made. So if you're using paints, you could take one color and another color and mix them, and you would come up with the color in the middle, which is cool. I mean, I like that. So back to our website. Okay. And it goes into differentiating between additive and subtractive colors. I found this really interesting. I mean, I didn't know actually why there was different types of color tables until I did this honor. But this is a little history. The next stage goes even into more in-depth on additive, secondary, subtractive color. Stephen Westland, professor of color science at the University of Leeds in England, breaks things down into a simple term in an email he called. We see because light enters our eyes. Okay, we know that. He says light enters our eyes in two ways. Directly from light source, like I assume like light, any kind of light, and reflection from an object. A reflection object would probably be something you see, like a lamp or whatever. This leads to the type of color mixtures of additive and subtractive. We have retained the British spelling of the word color here. Both systems are accomplishing one task, says Mark Fairchild. This is another professor, directed a program of color science at the Munsell Color Science Laboratory at Richester Institute of Technology. That is to modulate the response of three types of cone photoreceptors in our eyes. I didn't know that. Those are roughly sensitive to red, green, and blue. So these little sensors in our eyes can pick up those colors. The additive primary do this very directly by controlling the amount of red and green and blue light that they will see, therefore almost directly maps a visual response. The subtractive colors primary are also modulated red, green, and blue lights, but a little less direct. So one goes straight in your eyes and one is kind of a reflection from an object. Additive colors. This is what it says about what additive colors is going to be. Here is some facts found on the internet. When Isaac Newton was 23 years old, he made a revolutionary discovery. By using prisms and mirrors, he could combine red, green, and blue, which is RGB. I didn't know that before I did this. Regions of the reflective rainbows to create a white color. Newton deemed that the trio of the primary colors, since they were basic ingredients, needed to be created for the white color. Additive colors are those which make more light when they are mixed together, says Richard Rasmus. There's another professor. A simple way to think about additive light is to imagine three flashlights projecting individual circles of light onto a wall. The shared intersections of the two flashlights circle is brighter than the circle itself, and the third flashlight circle intersection will be brighter still. With each mix, you will be adding lightness. Therefore, we call this kind of mixture additive light. According to Rasmus, imagining each flashlight is fitted with a transparent color filter, one red, one green, and one blue, is the key to outstanding additive colors mixing. When the blue flashlight circle intersects the green one, there is a lighter blue-green shape. He says, spoilers, we're about to get into the secondary colors. It's cyan. The red and blue mix is lighter too, a beautiful magenta. And the red and the green also makes a lighter color. The surprise to nearly everyone who sees it is yellow. So red, green, and blue are additive primary because they can make all other colors even yellow. When mixed together, red, green, and blue lights make white colors. Your computer screen and your TV work this way. So if all three colors are put together, they're supposed to make white. Oh, look at this diagram I have here, this picture. We got red, green, and blue, primary colors. Now, the colors that are made in the middle, the yellow, the aqua looks like, and the purple, do they call it aqua? Let's go back up a little bit. They call it orange. So this is a different one? Red, no wait, we have red, green, and blue. Ah, that's a different chart. This must be. Yeah, that's a different chart. But as you can see, is the red, green, and blue, RGB, when they are totally interacted, they give you white. But the range or gamut of colors that can be produced from these three additive primary varies depending upon the primary colors. Most sources will tell the red, green, and blue are the additive colors, as Newton originally proposed, but Weston says a lot more complicated than that. It is often written that RGB are optimal because of their visual system has receptors in the eyes and responds optimally to red, green, and blue lights. But this is a misconception. So now the internet is disagreeing between each other. So we go on down and say, why is it a misconception? He says, the long wavelengths, sensitive cones, for example, has a peak of sensitivity in yellow, green, and part of the spectrum, not the red part. So that's what makes the difference. Well, I'm not a doctor, my friends, but I do know that there is two different colors, and this is our additive color. And now the next one is subtracted color, and it's mixed. And we say, enter the subtracted color. Subtracted color is mixing results when we mix together paints or ink. Well, you know what? This is what we're going to be using because dye is like an ink. So we're going to be using this, the subtractive colors. Subtractive colors mixing result when we mix together paints or inks. Weston says it relates to all the colors we see non-emission objects such as textile, paints, plastic, ink. These materials are seen because they reflect the incident light that falls upon them. I don't know why there's a difference in the lights, but it's like our printed paper or ink and stuff like that. And then it's M, Y, and C. I think they had an abbreviation for this. Where is it down here? It's not on this one. I don't see. But those initials, there's a K in it. And as you can see, when you mix these colors, and it's probably Magellan. Let's see, go down my list. It's probably, let's see, a piece of white paper, for example, reflects all visible wavelengths. When yellow ink is added to the paper, it absorbs the blue wavelengths, subtracting them from reflective light. This results in a perception of yellow because the paper now reflects the remaining non-absorbed wavelengths. You can see the green, the blue, right here in the middle. Right in the middle where it said right above the black, we have a green, a blue, a red, almost like the RGB, you know, red, G, green, B, blue, inside of this one. And subtracted color makes the color starts with a wavelength of white. When it's subtracted the specific wavelength, the primer is added contrary to added colors. So we're going to go down. So the distinction of the color systems really comes down to a chemical makeup of the object involved in how they reflect light. The additive color theory is based on the objects that emit light, while the subtracted colors deal with materials like paint. Subtracted colors are those which reflect the light and are mixed together. Raceland, when an artist paintings are mixed together, some light is absorbed, making the color darker or duller in the painter's color. Painter's subtractive primary colors are red, yellow, blue. These three hues are called primary colors because they cannot be made with mixtures of other pigments. So, Corellas and Googles aren't wrong. In the material world, red, blue, and yellow are the primary colors that can be combined to create additional colors of rainbow. But if you're talking about anything tech related, as much as most of us are these days, remember that the primary colors with TV, computer screens, mobile devices, and more all subscribe to Newton's light emitting color system. So their primary colors are red, green, and blue. Now, if I haven't confused you totally by now, I'm surprised. This section, which talks about the color mixtures of primary, grading, secondaries, additive and subtractive colors, is all good theory. But remember, this tie-dye honor is basically to understand what you do during tie-dye, all the way from preparing it, creating soda ash or urea or paints, colors, inks, combinations. The color is probably where the flair of everything comes. That's where you get a chance to make something color orientated towards a direction. You can be creative like a Michelangelo. God wants to see the creativity in us, wants to see us grow in our wants and our desires for something beautiful around him. He gives us this world of beauty, and we go out and destroy it by bombing it and fighting and just fires and everything. I mean, God gives us and we take. But when you're doing these colors, you can be creative. you can make a unique color. You know, Crayolas come with like hundreds of different shades of color, and it's all based on how they mix these colors. Primaries with secondaries, getting you different range of colors. So I'm going to put this chart on the link, and I'm going to go out there and look to see if I can find you some more color charts. It'll be under the color headline, under the extra links on the main page of the tie-dye. And feel free to use it to help you understand what kind of creative colors you would like to do in the tie-dye that you're about ready to do. May we see you in the next stage. God bless you, Mr. D.